one is a fusion facility of atomic molecular data, and each one has very different tasks. I don't think there is anything like a generic user of these data, and not even a generic set of data that is needed. It's very much on the application, and So, and I'm one of that group. And the only thing that is common to that group is that nobody of them is an atomic or molecular physicist. So, and over the last decades that I was involved in applying, amongst other things, atomic data also in studies, is always necessary, has been necessary and possible to have direct access to translators, to people between those two communities. Translating the terminologies and the concepts and boiling it down for dummies like ourselves so that we could try to get something out of it. In my case, most of all this was Ratko Janev, who spent a lot of time also in Munich, but also others who are not here. Takashi Fujimoto in Japan and Sonny Greenland in England and others over various periods in time. So these people have taken the pain to try to educate us, not really in atomic physics, but at least up to the level that we could try to apply these things. So I cannot contribute anything to uncertainty of theoretical data because I cannot judge at all. What I've decided to do is just tell you the story what in the application of atomic and molecular data for the ongoing design and construction of ITER. What is being used and how? And then you judge whether it's right or wrong and give us advice what to do and what not to do. First thing is, and I will start general and get more specific in a few minutes. First thing, of course, that the role model is the sun, and in the sun we have the fuel, which is photons, with a reaction time of the order of billion years, and we don't want that long, so we go to another fuel. The fuel in fusion is deuterium and tritium. So these are the atomic and also the molecular species that magnetic fusion is most interested in. It's atomic and molecular isotopomers, isotopes and isotopomers, deuterium and tritium, fusing to helium. These are the principal elements that fusion is interested in. And at temperatures of, in the center of 100 million degrees, so 10, 20 keV, hotter than the sun, because the reactivity has to be larger because the system is smaller. So I found this picture here recently explaining the life cycle of the sun, which is our role model. And here, that's where we are right now, roughly, probably, as far as I know, 4.5 billion years along from birth. And then there will be eventually the red giant phase when helium has accumulated and then a collapse. And this whole story will take about 10 billion years. A fusion reactor, this will be 100 to 200 seconds. So that is just because of the different reactivity, higher temperature, the scales at which fusion reaction, if a fusion flame is going to burn on Earth, then it will undergo this cycle if we don't take any action in 100 to 200 seconds. And that will mean there will be no flame. It just after it's being ignited, it's choked by its own ash. That is the reason. This is a simple reason why the fusion community, to a certain extent, is also interested in atomic and molecular data, because the way out here is to channel the plasma to the walls, deliberately produce plasma surface interaction and pump it from the walls away and replenish the plasma with fresh fuel at another place. So this brings into the fusion this plasma surface interaction, atomic and molecular physics. In addition, of course, there is the spectroscopy, plasma center, and so forth, but I'm not speaking about that. So this is currently the largest fusion device, magnetic fusion device operational. It's a JET, Joint European Torus. And actually in the mid-90s, this has, we would call it the proof of principle, that this particular magnetic confinement concept does work. And it did produce exactly the amount of fusion power, in that case 16 megawatts, when it was operated with tritium as predicted. So we believe that we have a proof of principle, and the problem is now to maintain it for steady state burning flame. And this has to be done such, we have to remove the helium permanently, otherwise it will not be a steady flame. And this is done by channeling the plasma magnetically to the bottom, in this case it's the center here, called diverter, and that's where you see light. That's where there is all the emission from not fully ionized particles, and even neutral particles. So the action of plasma surface interaction is deliberately channeled to the bottom of the machine. There are high heat flux components and pumps to pump out the whole plasma and replenish it with fresh fuel outside. The conditions, well, these are technical boundary conditions that we are facing here, and they are the same in many other disciplines. For example, the power load, which are believed to be acceptable here in a steady state device with current cooling technology and surface materials that to the extent that they are known, is about 10 megawatts per square meter. This has to be maintained here, or less. And in order to avoid excessive erosion, plasma temperatures also similar to that at the nose of a re-entering space vehicle of 1, 2, 3 electron volts. This is the past. This machine was, until last year, operated in Jülich, Textor, a small Programmat. You can see person here, very hard to get in. Then this is a machine where we have just had a look inside. They can easily walk around here. And that's the machine that's currently under construction, ITER, and this is not standardized. That's a person. This is how it looked when you look on the web now, today, or last couple of weeks. So the office buildings are more or less ready. Further buildings are under construction. This is going to be the Torus Hall, and the basement is now made, and now the construction is upcoming, and maybe in 5 years or so, this will then start operation. In this machine, yeah?
Side question. Is the funding all arranged for ITER, or at least the promise of funding?
Yes, this is, well,
annual funding.
Yeah, this funding, but the problem is the ceiling of that funding. It's the cost increase. So,
Yes,
but in principle, yes, it's not going to stop in the middle. Well, who knows? This is politics. Yeah, I think one wouldn't start to. This is, as they tell us, this is the largest construction site on Earth right now, and they probably wouldn't do it if the funding would stop like next year. Maybe 1 or 2 of the partner states. There are 7 partner states all over the world, and that may cause. Yeah, I don't know. I shouldn't comment on that.
It's above our pay grade.
So anyway, so in this machine, the conditions are here. You see this person again, and now I will always often showing such graphs here, and this is just a slice taking out of the torus. You have to think of this as a big toroidal or donut-shaped thing, and what we are looking at is just one slice of it, because it's essentially toroidally symmetric, and everything, every physics and everything that we discussed in a certain approximation can be looked at in such one section. So the goal is, and the target is, to produce 500 megawatts of fusion power. Then of that will be about 20% will be in the helium, and the 80% in the neutrons. The neutrons go out. We don't lose interest. Then lose interest. That's a neutron. That's eventually what is producing the heat for conversion into electric power. And this 100 megawatts, that's the heating power from the plasma itself. So once this plasma has reached these conditions that the fusion reaction sets in, then it will heat itself. It will burn like a flame, and only fuel is added. Or make a little bit heating here, external heating to control temperature and so forth. But in principle, it's like an oven where you just put fuel in. Once it's ignited, once it starts burning. And of course, then this is the issue. Then now, if you want to have this self-heating by helium, then we have to get rid of the helium, because that within 100 or 200 seconds accumulates in the flame, and the flame is choked by its own ash. And this is why the concept is to channel the plasma flow down into a particular designed region, which is called diverter. It's the exhaust of the system. And the plasma is channeled, a rather powerful plasma, to targets, and that's where the atomic molecular processes then start to play a role. Just last week or 2 weeks ago, I was speaking at another conference about, for me, strange subject, but it was about molecular processes in fusion. And I've shown this list. when I started to work in fusion, the sheer existence of molecules was not accepted. This was about 30 years ago, and gradually more and more came into the concepts. But right now, and that's what I'm trying to show, is that the concept of operating a machine like ITER relies upon certain set of molecular processes to protect the divert or the exhaust from its own destruction by the plasma. And this is what we call the diverter detachment regime, and this involves, written down here, hydrogen, but what I mean is deuterium, tritium, isotopomers, whatever the composition will be. There were other molecules which played an important role, but in these present days or years, fusion is losing a little bit of interest in hydrocarbons. Maybe they will come back in 10 years, I don't know. We have looked a little bit, but that's on smaller devices, into helium-3+. They are probably irrelevant in this type of fusion plasmas. They are probably rather relevant in small plasma devices used to study isolated aspects, plasma surface interaction, but not in a fusion reactor itself. That's at least the current thinking. Instead of hydrocarbons, attention has recently been changed towards beryllium hydrides, because the walls of the biggest fusion devices, ITER and JET, are beryllium, the main channel of walls. Nitrogen is used currently in fusion devices a lot for cooling the plasma in the edge. Deliberately injecting nitrogen, of course, when it's injected, it's molecular, but whether the molecular phase has any active role, or whether the molecules are distracted within millimeters and then it's atomic, this is not clear. So the importance of of nitrogen molecules and their fragmentation and what collision, electron collision and so forth is not, it's not established. We know that just that these molecules exist. So I will mainly focus on this first topic and try to explain why and what is happening here. What is the role of molecules? And then, if time permits, also speak a little bit about the others. So if we look at the center of the plasma, 10-20 kilo electron volts, there, of course, all chemical bonds are broken, and the whole area of atomic physics here is spectroscopy. So whatever is there as impurities or helium ash, well, helium is fully ionized, of course. Also, the light elements are fully ionized, fully stripped in the center of such a device, but tungsten not. And from a certain size of the atom, when it's heavy enough, it may reach the center not yet fully ionized. And that's why it's a target of spectroscopy to understand the transport of impurities from the walls into the machine. And there, it's the issue of diluting the fuel and cooling the fuel by radiation. So, but this is spectroscopy only, not no molecules there yet. If we look further out at the outer part near the walls, and we make the simple particle balance, and we have a flow across the magnetic field indicated by these arrows from the center to the core. We have, distinct from the center, powerful flows parallel. These red circles here or lines are projections of the magnetic field. And what develops here by self-organization of the plasma are powerful flows, the origin of which we don't yet fully understand, but that's the main challenge, one of our main challenges. Powerful flows down here into the diverter, and that's where the plasma material interaction is. If you make the balance up here in the midplane, if there is not a gas path or some deliberate perturbation here, then it's essentially a balance between the parallel and the cross-field flows, and still not much role of atomic molecular physics. But if we go down, follow the flow into the diverter and make the same balance here, then we see here it's really a balance between parallel plasma flow, powerful flow, up to the sound speed, with whatever is there, friction, interaction, with electron impact interaction, or so whatever the processes are that take place when there are molecules and atoms present in the plasma. I should say the focus really presently in fusion is to understand these flows and take as given that we fully understand atomic and molecular physics. That's why often in my community there's little interest in atomic and molecular physics. But if you look at the Mach numbers of these flows, this would be called a hurricane, essentially, the origin of which we don't know. And this is driven by electric fields in the plasma, by curvature effects and so forth, and maybe partially by turbulence. So that's what we need to understand, and well, we need to understand all of it. But the focus is right now on understanding these global things, except when there are particular diagnostics. In parallel to these major questions, there's of course many scientific questions to sort out all the details that might play a role, like the gas pump experiment that David has been showing yesterday. That's a very detailed, precise piece of science, which is also part of the game here, but it doesn't influence the design of the machine at that point. So, yeah, I think I can get it. Now, just again to get used to this geometry. So we will be talking about such a device, a torus, but we will be looking only at one slide all the time. And this is now I have, this is a slide where I can tell you what I'm mainly busy with. It is that set of equations here. This is a composition of hydrodynamics or magnetohydrodynamics. So continuity for the electrons, ions, impurities, momentum balance, that's the Navier-Stokes equations in a magnetic field and involving electric fields as well. And then there is an energy balance equation, which has even a few more terms: advection, convection, thermal conductivity, and so forth. And in each of these equations, there is this red little box. It is the sources and sinks, and these are the terms that come from the interaction of the plasma with the neutrals and with the molecules and with the surfaces. So this is essentially, and to illustrate a little bit here, what I've said already, when we focus now on this outer part of the machine, and in particular later on this diverter part here, we have, and that's given from the fact that in here there should be a burning plasma plane, so we know which fluxes come out, what the temperature roughly is here at the inner boundary. That's the boundary condition, and from there on the flow calculation starts. And when the plasma flows to the target, of course, there is erosion, there is this plasma surface interaction. Yeah, if you will follow the magnetic field down here, that's where the most intense plasma strikes the surfaces, and whatever is eroded there, sputtered chemically or physically, and gets ionized will have a tendency to either flow back along the magnetic field and then eventually go into the plasma, or being hopefully trapped by the incoming flow. So we have two kinds of major forces here, keeping hopefully the plasma clean. One is the friction with the incoming flow. That's a good force that keeps the impurity and the plasma surface interaction localized here. But then in the plasma there's a thermal force which makes heavy particles move up to higher temperatures, quite distinct from ordinary gases, where it's the other way around. So everything that's heavier than hydrogen will, by this thermal force, be driven up the temperature gradient to the center. That's a bad force. And that's a competition between those two that will eventually decide whether the plasma stays clean here or whether the erosion here will not only damage the diverter but even pollute the plasma to an extent that it doesn't burn anymore. So that is this. Up to now, it's only essentially it's continuum mechanics. And then, well, there are maybe gas puffs here, local perturbations, but then this is the part where the neutrals and the atoms and the molecules are. They are in these conditions, not in a continuum approach, they have to be treated kinetically, ballistically, because their motion, as you can see here, is, well, they travel large distances across gradients, and so they are quite distinct from many other plasma applications where the electrons are treated kinetically and the gas is more in a fluid description. Here it's the other way around. So the electrons are, and I will show an estimate in a minute, the electrons are well thermalized, and we have a continuum description for them. And the gas itself, it behaves kinetically. We have to describe that on a microscopic level. We use a code which is basically a combination of a fluid solver, which solves ordinary fluid equations numerically. Then it goes into atomic data pre-processing modules to condense the data in such a form that we can digest them. Then it goes into a Monte Carlo neutral particle codes. You have heard about Vega yesterday here in the US it would be called Vega, in Europe it's Irene. And this produces this calculates in a Monte Carlo fashion the neutral particle plasma interaction, and this provides these little red boxes in the system of equation, and then it goes around. So until it's converged. And now we have also a problem with convergence. As I've learned here, there's a problem with convergence in this community as well. We have also our convergence problems unsolved again. And a fluid calculation is standard, and we know how to judge about quality and so on. The same holds true for our Monte Carlo calculation. We have statistical estimates of the error bars, and all that's fine. But consistent calculation involves a cycle of going around 10,000 times or so. So it's a coupled scheme of non-linearly coupled scheme, and for this we do not have solid criteria about accuracy and conversion. So many of the concepts that have been discussed here in the framework of atomic and molecular physics, we also have, but at a different part in this kind of schemes here. Well, we probably also have them with the atomic physics, but this we take for as known, at least. And also when we look at atomic data now more specifically, then we can ask, how would we like them in these codes, in these modeling applications? And there is roughly a distinction how, if we go further to the plasma center, let's first go further out, near to the ball, then the behavior of the whole system becomes more microscopic, of course, and tiny aspects play a role. And of course, then the atomic data that go into these simulation and applications become, might be more microscopic, cross-sections, differential cross-section, and so forth. And if we move up further to the plasma center, then they get more average, condensed, bundled, and in the end, it's the center of the plasma. They are very crudely condensed, hopefully correctly condensed, at least fluidly correctly. Yeah, so that's, and in this edge region where we are busy with calculating the plasma flow and the lifetime of the machine, of the diverter essentially, we are just at the border again, where, it's not so clear to give a straight recommendation how far to condense the data. I would always prefer data as unprocessed as possible, because the condensation is often not a difficult task to do. I mean, we all know how to integrate a cross-section in a rate coefficient, even without knowing anything about atomic physics. That can be done. Or even putting rate coefficients into a collision radiation model. That's just a matrix inversion. I think this we can do with complete ignorance of atomic physics. What we cannot do is get the cross-section right, and how it extrapolates. So that's a border here. I have a short movie here. This is just to give you an indication about this concept, which currently is being used to design ITER and also power plants. And what is shown here is in this lower diverter here, the plasma temperature field in the color coding. Everything white we are not interested in. That's hotter than 100 million degrees. But so we are interested here in the plasma near the surfaces. That's where molecules and atoms exist of these light elements. And what is observed experimentally and also with these kind of calculations is that if we look at such a temperature field and we ramp up the density in a fluid gas by a gas pump or by any other means, we just increase the density. What one would expect that is, first of all, that the flux increases to the walls. And if that movie works here, this just shows this temperature field now as the density of the main plasma is ramped up. And the surprising thing, and this is known only since 15 years or so, is that the plasma, that's the temperature field, starts to detach from the targets. It withdraws itself, so the hot part of the plasma, which is the red part here, detaches from, it gets cold here, and an area of cold plasma is formed. And this is the operational scenario which is currently envisaged for a fusion reactor. To operate it in such a configuration, density, temperature, and whatever knobs we have, such that the plasma does not fully reach the target, but just marginally starts to withdraw itself and form here a cold, dense plasma, and that's where we are in the same energy range as planetary science technical plasma applications, 1, 2 electron volt plasma, just at a very high electron density.
So these simulations, the plasma becomes cold by through recombining.
Yeah, I come to it. That's a mystery. Well, it's not a mystery. We can say what's happening in the calculations, and we can say that the phenomenology is the same as we see in the experiment. What is the real cause, the microscopic cause, whether that's recombination or friction or what? Well, this we have to, for this we rely upon atomic molecular.
No, I'm only referring to the simulation.
Yeah. I saw in the simulation where it comes from.
Isn't the kind of simulations that require 3 months of computer time?
This was easier because it was for jet. This requires only a week or 2. But as the machines get larger, with the same, not the grid size in the calculation, if you keep the calculation the same, just make the machine larger, the problem becomes more stiff. So the timescales of various processes, plasma flow and atomic molecular processes, get more disparate, and that makes these codes slower and more unstable and so on. Yeah. So this is just the genealogy of the ITER diverter. So this kind of calculations have been going on now. It's almost 20 years, and the design is changing many times. And now it has boiled down to this final design, more or less final. And this is, in here is a learning curve. First of all, with respect to what we learn from experiments about the behavior of this system, and also from codes, plasma flow calculations, and atomic molecular processes. They change. Sometimes they do have a significant effect on what this thing looks like, and we have to get that right at least, because that's the only thing which we believe is known. But when I listen to what this audience is, then I know so much. Okay, detachment. Just to again indicate where the plasma conditions. So in the core plasma, we have densities in excess of 10 to the 14, plasma densities, electron densities, and in the diverter even a little bit higher, up to 10 to the 50, so it's 10 to the 21 per meter. The temperatures in the core, 20-25 keV, so that's a battleground for spectroscopy. On tungsten, for example, and then in the outer layer here, in and up into the diverter gets colder, and this is really blowing up this thing a little bit. So we form a dense plasma in the diverter, set often to a large degree constant along magnetic fields, and a rather cold one. I will check this picture here in another scale now, from only 0 to 50 eV, really tells you that what we have seen in the movie before, and this is an ITER calculation. This is one of the calculations that takes 3 months. That here it gets really down to below 5 eV temperatures. What I wanted to say, indicate here, if you take these densities and these temperatures and estimate the electron thermalization time, this is very short, nanoseconds, and the mean distance that an electron travels before it thermalizes in that plasma is a centimeter or so. And we are talking here about, well, up to meters. So that's the reason why we often assume, with respect to electron collisions, that the plasma is thermalized and we take Maxwellian distributions. For the electron-ion thermalization time by Coulomb interaction, this is about 1,000 times larger, but still very fast compared to other time scales. Here, the lifetime of an ion in the edge of this whole device, so that it's still, and that's a result of the calculation, but it results also from a simple estimate of the equilibration time of the ion and electron temperatures, that they are the same, roughly the same. You wouldn't see a difference here if I go back and forth. They're not identical, but very close. And that's another difference between many other plasma applications, technical plasma applications, where the ion temperature is typically very cold and the electrons are hot. But here that's the same, close to the same. The pressure, and now we come to the reason why this is detaching. We have, in order to find out why we look at we look at the pressure here, the pressure field of the plasma, and I have to expand this region twice to really indicate what's happening. First here and up here, then we wouldn't see much. But if you take a very close look to the 20-30 centimeters near the target, then what we see is that the plasma pressure in the direction along the magnetic field drops suddenly in front of the target, 10-20 centimeters in front of the target. And this pressure drop is what is behind this detachment of the plasma away from the target that we need. So if that would not happen, then ITER will not work. So it is this detachment phenomenon that we rely upon, and there are many terms contributing, but the dominant ones are, of course, the pressure gradient being balanced by chemistry, by whatever friction with gases or elastic or inelastic processes we have. This, up to this point, could be either recombination, so a loss of plasma momentum because the ions disappear, they recombine, but it could also be a friction of the ions with a cloud of molecular gas. So anything that removes momentum from the plasma flow close to the target will bring about this state. Looking at the neutrals, up to now this was electrons and ions. The neutrals, that is the atomic component in this simulation. Yeah, you see already here and better down here in this larger view, they stay outside the plasma. They form a layer, 10 centimeter, and the molecules maybe 5 centimeter wide layer. It's around the outermost part of the plasma. If you go to smaller devices, this size of this cloud stays the same, but the plasma gets smaller. And so the smaller the plasma gets, the relative larger this effect of the neutrals and the molecules. And so the larger the plasma gets, like here, the more it shields itself from the atomic and molecular physics, and it becomes a boundary layer process. So we are talking about really boundary layer phenomena given the total size of the machine. So what is being formed here really is a cushion or a layer of atomic and even narrower layer of molecular. This is H2, but it means D2 in this calculation. Gas which is going around the machine everywhere, but it's localized and most strongly in the diverter here. And at the bottom of the diverter, I haven't indicated it here, but there are these pumps. And it's this, in the neutral form, this gas can get pumped and can be refreshed by new fuel, which is typically done upside at the top of the machine. So by this mechanism of pumping, the neutral gas here, which is formed by the plasma by recombining at the surfaces, and puffing fresh fuel up here, we produce a convection in the flame which flushes the flame from its ash. And the hope is that this can be achieved without destroying the vessel. We have to have an intense cloud or cushion of gas still here because it has an active role in protecting the structures. And at the same time, we have to pump it. And so these are conflicting requirements. So if we pump too much, we can get easily the helium out, but then we lose this protective action here of the gas cloud, and it will destroy its own vessel. And if we don't pump, we don't have a problem with erosion and with heat load, because the gas protects it, but then the plasma gets choked by its ash. And so we have to find the operational window, and that's the challenge that we are involved in. It's not a very detailed, specific science question, it's more a global question whether this can work or not. What we also see here when we have molecules, this narrow cloud here, we also have molecular ions, and these are even narrower. They only exist inside the plasma, not in the vacuum region around, where there's only neutral gas. There's a very narrow layer, and I had to change the color scale here by 2 orders of magnitude to make the H2 plus component visible at all. Which means, and we have to remember that we have electron densities of 10 to the 14, 10 to the 15 here, and H2 plus densities of 10 to the 12. And that simply means, as far as I can tell, that there will be no production of even H2 plus. At least that's the assumption, and I think this is, well, I don't know. I guess it's not too bad. Now the molecule as it looks like in these calculations is very simple. I am almost embarrassed to show you. I'm thinking about removing the slide, but I should show you what we are doing. In our our molecule looks like this. The same for use the same setup for all isotopomers. There are a few vibrational states in the ground state, not states, not modes, but the energies. So we look at vibrational energies. We use the same for deuterium and tritium, but it's only the vibrational energies that are considered. Then there are a few states here, n equal 2, n equal 3, singlet triplet system, and there are, collision radiative models have been set up since 10 years or so, mostly based on educated, more or less educated guesses about the transitions between these states here, hydrogen-like up here, helium plus-like, I think. And then a few more or less well-guessed excitation rates from vibrational levels to these excited states. And the heavy particle processes that are included here is just proton collisions on this vibrational spectrum of ground states, just in order to capture the resonance between stuff in hydrogen, roughly B equal 4 to H2 plus, to get the ion conversion right, the charge exchange right, because this is a key player providing volume recombination. As soon as we have put molecules in a plasma, plasmas have a tendency to start to recombine because of this ion conversion process here and then subsequent dissociative recombination. So this is what we use. We know from others that more is known and is probably needed, and the challenge here really is to find out how much is needed, how definitely when we do small plasma experiments, isolated plasma studies on linear plasma simulators for specific purposes, then these kind of models, and even, I don't know how far they have to go, have to be used. When it then is condensed into something that is used in a global fusion code, it's condensed in typically these simpler forms, and then the hope is that we have missed out major things. And this problem of condensation without losing too much information, this is the challenge here. But this requires, of course, knowledge of the right system, the correct system, in order to condense it to something that is still physically correct. And my chair lady is indicating that I should stop, and I can stop anytime. Maybe here.
1 minute.
And this is setting up such reduced models. This is right now a major activity here. There we are often relying on the data sections, on the nuclear data section, and this, in particular on people like Bas Brahms and Huon, and earlier what was Bob Klar, and before that Radko, as a guidance to find out what is the correct thing, and then we try to find out how we can condense it without for particular applications. And maybe applications where it cannot be, we have to use the full thing. Often these are very detailed questions, but and sometimes we have to find reduced models, emerging laws. And this is a major activity. And I think I won't be able to get to the carbon story, but maybe just tell you that up until last year, October, I have spent, together with Radko, maybe 10 years working out a hydrocarbon database. And then came the decision by ITER to eliminate carbon from the machine. This has a simple, I skip all this. The simple reason why carbon is being eliminated is already 15 years old, but the solution has not been found since. When JET was operated with tritium, then the cumulative tritium input, which is this scale, and the tritium inventory that was building up in the machine over those discharges, this kept increasing without any sign of saturation. And not only this, the location where the tritium was recovered after that campaign was surprising. The tritium was not recovered in the tides which were exposed to the plasma, but in very remote areas. It had fallen in form of dust and all kinds of things to very remote areas. So they must have there, at that time, it was clear that there are transport pathways of tritium in form of hydrocarbons, embedded in hydrocarbons, which play a major role here. And over the years, well, then we have set up this database and so forth. And over the years, really, the fusion community has become skeptical about tritium because ITER and a fusion power plant is a nuclear site, and there is just by nuclear licensing, there is a limit of permitted tritium on site. And in ITER, that's 700 gram by nuclear licensing, and that would mean if this accumulation that we see experimentally and as also indicated by codes would be reached within 100 or if we are optimistic 200 discharges only, and then it would mean shutdown of the machine, major cleaning, 1 or 2 years stop and so on. That's not acceptable by for $50 billion machine. And that is the reason why this is now changing to tungsten. Yeah, this was a plan to start ITER until last year, to start with carbon, and then later, when it comes to the nuclear phase, you start with in a non-nuclear phase, 5 years or so, with the carbon to learn how it works, and then to move to a full tungsten device. But yeah, it was not October, it was November. The ITER Council has decided now to skip that carbon phase, and now it will be ITER will be starting with full tungsten whenever it starts. It will start without carbon. That has been the decision, and that has now moved the focus with respect to hydrocarbons, away from hydrocarbons, but to beryllium hydrides, whether not much is known about them, and whether they will have similar problems, probably not, maybe not, hopefully not, I don't know, but that's roughly the story.
Thank you.